So we're going to work with rational functions. So the first thing we should do is we should actually talk about what a parent function is. A parent function would be the representation of some function. So you've probably worked with quadratics and linear before. It would be like the simplest form of that function, okay? So a rational function could be something like this, 1 over x. And that's the algebraic way of representing it. So in math, we have lots of different ways of representing things. We can represent algebraically. We can represent graphically, okay? And what's a good idea is getting into the habit of, anytime you don't understand something, try to show it algebraically, try to show it graphically. You can technically make tables. There's like a couple other ways, trying to draw pictures if it's a word problem. But getting used to graphing and algebra together really starts to give a lot of a clearer idea. So rational functions happen to have this type of relationship, okay? Kind of look like this. So that's what they look like graphically. What we're going to focus on, it looks like our goal here, is to work with the algebra, okay? This one's hard to graph. We're not experts at graphing it yet. So what we'll do is we'll work with it algebraically, and what we're going to learn is by putting, like for instance, this one looks like it's a quadratic on top and a linear on the bottom. If we're able to factor, it gives us a little more information about it, and then in the long run, that'll make it easier for us to graph. So we're really working on some algebra stuff to make graphing easier in the future. So when we take a look at this very first one, I have a quadratic on top. So what you might want to do is, it's not a bad idea to essentially kind of split things up. So I got a quadratic here, and I have a linear. And the way I know that is by the power of the leading variable. Okay, so this one's power of 2. This one has nothing. It's assumed it's the power of 1. What I need to do is do some factoring here. So there's lots of different methods for factoring. I'll do this one quickly on the side here. And we'll see if you remember different versions. There's decomposition, product and sum. There's like factoring by like this column version. Do you have a specific way you remember?
The product and sum and
Product and sum.
decomposition.
Awesome. Okay, so let's stick to that one. This one here, so for that, you're looking for, we kind of have to remember the standard form of a quadratic, which is ax squared plus bx plus c, okay? And the reason that's important is because what we're really looking for is we're looking for two values that multiply to whatever a times c is, okay? And there is a little shortcut to this one, but this is the general rule. We're looking for two numbers that equal that when multiplied, and then these exact same two numbers, when added together, are equal to our middle term, which is our b. So in this case here, I just have to make sure I can recognize my a and my c. So my a happens to be a 1, which makes multiplication really easy. It just ends up being, negative 18 in this case. We'll say that's equal to negative 18. And our b value happens to be 3. When going through this as a process, it's usually easier to find factors. There are so many versions of things that add to 3, especially when we start to use negatives. But there's really only so many whole number factors we can find. So 18, off the top of my head, 1 and 18, that doesn't really look like it'll add to 3. 2 and 9, those work, but I'm not going to get 3 out of those. 3 and 6 actually work out really nicely. If I use 3 and 6, okay, that gives me 18. And then 3 and 6, I mean, added together doesn't work. But if I find the difference between them, let's say that's negative 3, that will give me it. And if I look up here, this one has to be negative 18. And in order to multiply to that, we need a negative. That idea is common to you? Awesome. So then what's important about these two numbers here is this is where we start our decomposition. So I'm going to rewrite this down here. So I'm going in detail in this one. And then the next one we can kind of plow through this if this is a simple idea to you, okay? This positive 3x, what we're going to do is we're going to decompose it. Essentially, we're going to represent it like this. Think of it as we're splitting it into 6x minus 3x, which makes sense. 6x minus 3x actually just gives us 3x. We've split it apart. That's the concept of decomposition. The other two terms we're going to write, oops, that's the wrong one. We're going to write down, so x squared plus 6 and then minus 18. And then when we're working on our decomposition, we're looking for a common factor in the first two terms and then a common factor in the second set of terms. If I look at the first one, there's no coefficient here, so I can't really take a number out, but I can take x out. X would be a common factor in both of these. So in the next line I have x, and then whatever each of these divided by x are. So x squared divided by x gives me x, and 6x divided by x gives me 6. It works out nicely. In the next one, I can't divide by a variable, but I can take a common term. In fact, I can take out negative 3. If I divide both of these by negative 3, I end up with negative 3x divided by negative 3 gives me x, and negative 18 divided by 3 gives me positive 6. The way I know this has worked is if my two brackets are the same. If they're the same, I've done this correctly. If they're not, I've made an error. Technically what I'm doing is I'm now common factoring again from x plus 6 and x plus 6, but the easiest way, most people tell you from here as an algorithm or a set of steps, just make two brackets and put the one set in here, so the duplicates, these two, and then these two simple terms you put in the other one there, okay? If that was more of a review, awesome, but I just wanted to make sure we understood the factoring part. So what did we do that for? What was the point? The point was to find a factored version of the numerator. Think of this like a large division question. We're trying to find a factored version of the numerator. So when I go to rewrite f at x, it's still the same function. I'm going to represent it as x plus 6 and x minus 3. Okay, awesome. But then I have my denominator. My denominator here is still 7x minus 21. So when we take a look at this, this is not a quadratic. So the factoring this won't be as complex. This one, we're actually just looking for a common factor. So if I take a look at these two terms, I can quickly see that 7 comes out of both of these. So if I divide 7 by both of these, I end up with a common factor of 7 on the bottom. 7x divides 7, it gives us just x. And negative 21 divides 7 gives us negative 3. So that's my denominator. I've now put it in a factored form. I'm going to bring down the rest of my equation. So we have, there we go, x plus 6, x minus 3. Okay, this is great. I'm in my factored form. The question asks us to simplify. It turns out that if you have a set of brackets, think of this like they call it binomial, but if you have a set of brackets on both the numerator, so the top and the bottom, they cancel each other out. It would be the same idea as I'm going to write it here, as if I had multiplied by 2 and multiplied by 2. Well, I don't need either of those. That doesn't help. I just cancel each other out. In this case, the term is just a little bigger. They've decomposed the term. It's some number minus 3, some number minus 3. Because both of the x's will be equal, we can cancel that. Now, the second question that was asked there was, what can't x be? And before we cancel things out, it's actually probably a good idea to talk about this idea. What we have is multiplication on the bottom. 7 times some term here. There's a rule that you can't divide by 0. Division by 0 is no good. Okay, so we'll just give it an x here. Doesn't matter what the number is. We can't divide by 0 because it's undefined. So what we got to make sure is that we don't create a 0. 7 is great. Most likely won't create a 0. But their multiplication is really unique. You need to have one specific value to create a 0, and that number is 0 itself. So in other words, what we need is this little bracket here. We got to make sure it doesn't equal 0. Because if it does, we're going to get an undefined question. This is not going to work out for us. In order, or a way to do that, is just focus on the bracket itself. So the bracket here is x minus 3. We're going to set it equal to 0. And really what we're saying is 0, I want to do it in blue here. 0 cannot equal x minus 3. Okay, so I've used the symbol, it's a little different there. Does that make sense to you? You've seen that before? Awesome. And now I just have to isolate for 3. So I'm going to bring 3 to the other side. When I do that, it becomes just positive 3. That idea is okay? So in other words, what we got is x cannot be 3. That's going to actually be really important for us. That's going to help out quite a bit. Now that we've done that, we can go through the simplification process. So we'll keep this here. It's going to be part of our actual domain when we go to write the question. I'm going to rewrite it again, just because it got a little messy there with the highlighting. And we end up with 7x minus 3. Well, like we said before, these sets of brackets cancel out. So the simplified version of this is x plus 6 divided by, bring it down, 7. This would be the simplified version of our original question. Our original question, zoom out one more time, way up here, okay? This was the original question. We went through the process of factoring it. We figured out what x cannot be, so that's going to be part of our domain if we go to write it. And it turns out this is the simplified version. When x can equal 3, if we were to give it some graphical representation, what it's saying is that there's an asymptote. There's an asymptote at positive 3. So in other words, we have some relationship. Well, it's not very straight, is it? Let's try that again. We have some relationship where the graph looks something like this, maybe something like this. And it could be shifted up or down. We're not quite sure yet.
Yeah.
Technically, we can tell from what we got, but it's maybe not something we've covered. So at least that's a part there. This is that idea that x cannot equal 3. It will never touch that vertical line.